In 5.2, we looked at how the derivative, the first derivative, could be used to determine absolute maximum and minimum values on a closed function. We can see just by looking at the graph that we could calculate or find the critical number or critical point at both of these places where we see the function having a maximum or a minimum. In section 5.3, this first part, we're going to look at how the derivative tells us where the function is increasing and decreasing. As you look at this continuous function here on this blue part that I'm tracing, you can see that the tangent line would have a positive slope, right? All the tangent lines we could draw, or all the first derivatives we would find, would yield us a positive answer there, positive slope. Then as we tilt downward, I don't know why that goes straight, right here, you can see that the tangent lines to this part of the graph would have a negative slope, or our first derivative would be negative. Then you can see again that at that critical point B, the function would turn back up, be increasing, and any tangent line to this part of the function would have a positive slope. So we're going to see today how the first derivative tells us where the function is increasing and decreasing. This is how we write it in open interval form. So we can see here that it's increasing from negative infinity all the way to a, or it's increasing from b all the way to positive infinity, where the slope of the tangent lines are positive. Similarly, it's decreasing, we see, between a and not including a, because remember, at a and at b is where the derivative will be 0, right? The derivative will be a horizontal line, so we don't include it. It's open intervals. Between a and b it's decreasing, and that's where the tangent lines will be negative. So you can see the blue and red here. That wouldn't have shown on your note package, but you can see where the tangent lines are positive and negative. Below is a summary. So if the derivative of x is greater than 0, okay, if the derivative is positive, we know the derivative implies the slope. If the slope is positive, then the function's increasing. If the derivative is less than 0, so if the derivative is negative, if the slope of the function of the tangent line is negative, then the function is decreasing. And if the derivative, oops, I should change colors. If the derivative equals 0, that's the critical point. That's the place where the tangent line will be completely horizontal. This leads us to our first derivative test. You can highlight it in your note package. If c is a critical number, and we know how to find c then, we did that in 5.2. If c is a critical number, then f of x has a relative minimum if the derivative of x switches from negative to positive. Let's flip back a little bit here. You can see if the derivative of x switches from negative to positive, so the derivative was going down, it was negative, and it switches to positive, going up, this critical number here will be a minimum. Likewise, if you look at the bottom of your page 9 in the box, the second bullet, there's going to be a maximum spot if the derivative switches from positive to negative. So as we're going, the derivative here is positive, right? If it switches from positive to negative, then this spot will be a maximum. That makes sense. It's intuitive. On the top of page 10, start the examples. What we're supposed to do is find the open interval, so interval notation, on which this function is increasing or decreasing. We're also supposed to find the coordinates, so the x, y point of any relative extrema, okay, the maximum or minimum. So let's look at A. F of x is equal to -7. We know f of x equaling -7 is a constant, right? It's going to be a flat line. The derivative is 0. A flat line will never be increasing or decreasing. In fact, a flat line or a constant will, there's not even a tangent to it, right? The tangent is 0. There's no maximum, no minimum. It's neither increasing or decreasing. Let's look at number B. Okay, we're starting here from the simplest, A, and moving to more difficult. So this will be the next level of difficulty. We're looking at this function, f of x, and we can see if I would rewrite this, this is like 1 over x, or 1x over 2, subtract 6 over 2, which would be 3. This is a linear function, right? We've got the slope times x, subtract b, y-intercept is -3. The slope will be a rise of 1 over a run of 2. We can visualize this in our minds, and we can tell that this is going up, right? It's positive slope. It's got a 1/2 is positive there. When we take the derivative here of this, it will simply be a 1/2. Right? The slope of the tangent line will be a 1/2, the same as the slope. The tangent line is the same line. It's hard to have a tangent to a line. Usually we have a tangent to a curve. So we see that this is always positive and always increasing. We can write here that this function is increasing over the open interval from -infinity all the way to positive infinity. Okay, let's move to C. All right, this one is a little bit harder to picture in our minds, right? And see where it's increasing or decreasing, and see where our tangent line would be horizontal, where those critical points are. So this is a good one to do. Let's find the derivative and analyze it to find the critical points. Okay, derivative here, x squared plus x minus 12. You can pause it and work through that if you want. You're good at finding derivatives by now. So there's the derivative. We know that the critical numbers here, the critical numbers again are the spots on that graph which will have a slope of 0, okay, or where the derivative is equal to 0. So the places where the derivative equals 0, well, x squared is plus x minus 12 is the derivative. Where does that equal 0? Well, I could factor it and find the zeros pretty easily. Multiplies to -12, adds to 1. Okay, so we see here it's got zeros, or it will be 0 at x equals -4 and x equals 3. We know critical numbers also happen when the derivative does not exist. And in this case of a parabola opening, or it's a cubic function, this exists everywhere. It's continuous, so there's never, that never happens. What we want to know now is what's happening around or between these critical numbers. Is the function positive or negative? When is it going up, increasing, or going down? We also want to know, okay, is x equaling -4 a maximum or a minimum? We know that the first derivative test says if it's going from a negative slope to a positive slope, that would be a minimum. And if it's going from a positive or increasing function to a decreasing, that would be a maximum. So we need to figure this out. One way that we do that, or the way we usually do that, is sign analysis, to analyze the signs here to see where this is positive, increasing, or negative, decreasing. So let's do that. You know how to set that up. Go ahead and pause and do that. Okay, so the derivative of f of x then will be positive here. At 3 it will be 0, and then between it will be negative, -4, 0, and then positive. This tells us then that this function is increasing from -infinity all the way to 4, or from 3 all the way to positive infinity. Okay, and it is decreasing from -4 to 3. Remember, these are all open intervals. We're not including those zeros. That's where there's a horizontal slope. So that answers number 1. Now let's look at number 2, the coordinates of the relative extrema. We can see that here's the critical numbers. We found that the -4 and the positive 3. We want to know the points, their coordinates. So you're going to, and you can do this on your own, plug in a -4 into the original function and find the y value there, and then plug in a 3 into the original function. After you do that work, I can tell you that you get for -4 116/3, and when you put in the x of 3, you're going to get -37/3, which tells us that this happens at point x comma y, and this happens at the point 3x and y is -37/3. Okay, which of these is mins and which is maxes? Look back at your first derivative test. It says, let's look at the sign analysis, when the derivative is going from positive, so it's going up, and then turns to negative going down, that would be a max. Okay, that's this one, the max is here. Also, when the derivative is going from a negative slope, okay, so you can picture the function going down, turning to a positive slope going up, this will be a minimum. That's what the first derivative test said. This is the minimum. Okay, so I'm running out of time. Let's move on to the next example. Okay, so we need to find the critical numbers. We do that by finding the derivative. There it is. And then solving to figure out where the derivative will equal 0. Here we can see that x has to be equal to 1 in order for 1 minus this to be 0. Or looking where the derivative does not exist, and we see that with x in the denominator, x can't be 0, so it doesn't exist there. So these are the two critical points. Okay, sign analysis. We really only have the one factor here. We have the critical numbers of x being 1. That's going to make this factor 0. And we've got the critical number here of 0. We know that that makes this factor not exist. There's going to be an asymptote here. Does not exist at that spot. Okay, what do we know about the between there? If x is greater than 1, it's going to be 1 minus a larger number down here. So we're going to find that that evaluates to positive. If x is, say, 0.5, then we're going to have 1 minus, this it will evaluate to something bigger than 1. So this is going to yield a negative. How about if we have a negative for x? It's going to be 1 over something. This is evaluate negative. It's going to be 1 minus something. This will turn positive. It'll be a positive answer. Okay, so we can tell then that this function is increasing on the interval -infinity all the way to 0, and from 1 all the way to positive infinity, and it will be decreasing between 0 and 1. Okay, those are all open intervals. Now what we need to do is find the coordinates of these relative extrema. So let's put the critical numbers we found into the function, and you can do that and evaluate them. And then you need to decide which of these is a relative minimum and which is a relative maximum. You can look at these answers as work for example F. We're not going to do E together. Okay, so we found the derivative. We used that to find the critical numbers and where it doesn't exist because of the 0 in the denominator. We used the numerator and denominator to do sign analysis on the derivative, and found where it was increasing and decreasing, and then we used this critical number to find the maximum. Maximum, remember, is going from positive to a negative, yields a max. Okay, you can attack your assignment. Number 2 through 18 evens would be the regular assignment. And we will do part 2 of 5.3 next.